PostgreSQL project, and they just saddled me with this strange title called CFO of PG Experts, and now my self-promotion is done. So today I'd like to talk about trees. Who's tried to do tree structures in SQL? Who's liked it? Well, there's one in every crowd. Today we're going to figure out how to do this. But first I'd like to introduce something that needs to be in the regression test for your database management system. If your database management system can't make you one of these, it's insufficiently powerful. Everybody recognize it? Okay, so sorry? Yeah. Yes, as a matter of fact, I can in SQL. It's an amazing thing, but not right now. So, okay, I'd like to talk about a few of the current approaches to recursive structures in SQL, to trees in particular. So we have external processing, and anytime you pull something out of the database, that's sort of fail on performance because you just took you just spun the disk and then took a network hit before you started to do anything. There's functions and stored procedures. I don't know to what degree. MySQL, you can write functions in C, right? Yes? No?
Yes.
Okay. Materialized path enumeration, is anybody doing that one? Okay. So there's, we'll talk about that. Nested set, has anybody done that one? Okay. So some of the pros and cons. With external processing, you kind of get a lot of freebies. You get to, you get to use whichever language you want, and there's a lot of choices there. Downsides are the scaling, and then when you need to relate back to your relational operators, you're kind of stuck. You have to then re-import it somehow, and then sort of create your own database management system. So it's not that much fun. Functions and stored procedures, fairly easy to visualize what you're doing. It's usually pretty easy to write them, at least in like Oracle and Postgres. Again, the downsides, they don't scale very well, and they don't really know about, they don't really know that they're inside of a database. Materialized path, again, it's fairly easy to visualize. You have a single tree, and you have the path that goes from the root node to wherever you are right now. It's not that complicated. The problem is, well, there's several, three of which I'll mention here. You need to do data definition for each hierarchy that you want to create. So there's, it sort of takes away your ability to do queries ad hoc, because the people doing data manipulation generally don't have permission to do data definition. At least at the larger shops, they don't. Frequently, you have full table changes at each write with the materialized path. If you write at the wrong place, you could be rewriting the entire table, and you definitely have to be looking at lots of it. And again, it's hard to do relational operators because those paths are not really sort of relational things that you can really grab hold of with SQL. Okay, so nested sets. There's more upsides here. They're easy to manipulate on a select. They sound cool. They're endorsed by a famous bald guy. Does anybody recognize who that is? That's right, Joe Selko. Unfortunately, much as I love Joe, and he's a brilliant, brilliant man, and he's contributed a lot to the practice of SQL programming, he's wrong on this one. Again, you have this DDL for each hierarchy, so you've basically gone back to the tree structured databases that, you know, CJ Date was and EF Cod were reacting against when they created relational database management systems. You got the full table changes, and you still got the hard stuff on relational operators. In comes common table expressions. So I'd like to thank the ISO SQL Standards Committee. Has anybody read the SQL Standard all the way through? I was going to call somebody out on that one. Yeah, so they went into tremendous amounts of detail in a language that I haven't quite characterized. If anybody's got some idea what that language is that they write this stuff in, please don't tell me. I don't really want to know. Yoshiyuki Asaba was a gentleman in Japan who went and wrote all this lovely code for Postgres. Ishii Tatsuo, he did a lot of the sort of translating from English to Japanese and back, you know, linguistically and culturally, and all this good stuff that made the project actually work. Jeff Davis did some work on this. He was here yesterday. Greg Stark, Tom Lane, lots and lots of people. If I've forgotten any of them, it's my fault. It's not because they didn't do something really amazing. Okay, so what is it? Common table expressions. These are basically views which you can create in data manipulation language at runtime. Does anybody use the common table expressions from DB2 or Microsoft SQL Server? Is anybody still awake?
Does anybody still use DB2 or Microsoft SQL Server?
Yeah, surely somebody has. I mean, there's people in this room that have used them. I'm not asking about current, you know, what you're up to now. Anyhow, so this is a thing that originated with DB2. It's as I said, it's a way of sort of creating views not at DDL time, but at the time of the query. So they're like runtime views. Really powerful concept. And then, not satisfied with this powerful concept, the folks at IBM added another concept that you could use at the same time, which is recursion. So just generally, when you do a recursion, you start with an initial condition, and then you create a recursion step that refers back to that. And because you know, you could stop there, but because we would like to have some idea that the query will actually finish, you usually put in a termination condition. Okay, so typical example, we have a table of it basically shows relationships between employees and their bosses. So we're going to populate this table. We're going to define the top boss as the person whose boss is null. So we have an adjacency list, and we have one boss. Okay, so we're going to add some relationships in there. With the sort of multiple values insert. Does everybody see that one down at the bottom? It's in red. Basically, this creates a cycle in our tree, or in our putative tree. So you got to kind of watch out for that, and that's what I meant about putting in a termination condition. You want to be able to say, hey, wait a second, we cycle here. So now we're going to make a tree of these out of these relationships and display it. So we start off with a description of what this temporary view looks like. It says with recursive T of node comma path. You don't actually need to supply those right up top, but it's kind of nice because it tells you what you're looking at. So this is what the view will be. There will be a node and a path. Then we're going to say select, and then we're going to use an array constructor. Does MySQL have one of those? Array? No. Okay, well, it's a nifty Postgres thing, and I used it shamelessly because I'm talking about Postgres. So we put the node, and then we initialize an array with that node in it. So this is the top of the tree. And then we just find the ones where boss is null. So we want a forest, which consists of those which are the top bosses. Everybody clear so far? Okay, so that's our initiation. We're going to union all of that with the recursion step. So we select an ID from the employee table, and then we join it back to this T, this recursive view that we just created. That's how we're doing it. So we're joining it back from T to node, or from boss ID to the node. So you're saying we're finding all the people whose boss is the node above. So that's our recursion. We're materializing a path here on the fly. This is the fun part. The path goes away at the end of the query, so you don't have to store it. It can be more, how I say, it can be more efficient on the disk. Okay, and then so that's our recursion step, and we want to have a termination step. Does anybody want to tell me what this last bit does? Part in blue. Yes, very good. It prevents cycles. So does everybody see how that works? Does anybody not see how it works? Well, okay, so where ID not in t.path. T.path is an array of IDs. And and that's the materialized path that we created with this recursion. Okay, so we now have we've now constructed our result set, and then we want to sort of display it. And here's the display. This is basically using the array constructors. So if the array length is greater than 1, i.e. it's not a root node, do one thing. If it is, do a different thing. And all of that is sort of Postgres syntax that you don't have to worry too much about. So this is what we get. Okay, so that was a fairly easy problem. But common table expressions with recursion let you tackle harder problems, like, for example, NP hard problems. So here we have a traveling salesman problem. Anybody familiar with that one? Okay. So we have a traveling salesman problem. The salesman needs to start at one place, visit many cities, return to that place, and do so in minimal cost of whatever your cost metric is. Right. So here we have the XKCD version. Anybody follow XKCD? Okay, good. So you may have seen this one before. We're going with brute force here because, you know, I didn't want to really make this presentation about solving traveling salesman problems. Apparently you can do better with dynamic algorithms, and then there's the sort of eBay version. If you can find the eBay version, that's much better to do, but you can't always. So we'll make a schema, create pairs of cities with distances in between them. We're going to have a primary key of just the 2 cities, and then we're going to check from city less than 2 city. Why would we do that? That's right. We don't duplicate information. This ensures that you don't have a from and to and then a to and from that are conflicting. Now we're going to assume that the distance from, say, San Francisco to San Jose is the same as the distance from San Jose to San Francisco. If that turns out not to be the case, we just drop that constraint and populate more stuff in the table. Okay, so I picked some cities in Italy. You'll see why in a little bit. So we have cities and distances, and I inserted a lot of these. Okay, our traveling salesman problem. How are we going to solve it? Well, first we're going to make a couple of working tables that we're going to work with, and those things are going to be part of our programming exercise. So we have, with recursive, from city to city distance as, and then distance one way, and then we actually want those duplicates in our result set. Right, so you want to be able to traverse the graph whatever directions you need to. So we actually create the duplicates on the fly. Is everybody clear on this part so far? Questions? Too fast? Too slow? Okay. So we're going to start with all the paths that you could travel. Then we're going to start. We're going to start from a city, and right. So we have a from city, a to city, a distance, and a path. Now we're going to get longer paths. So those were just like pairs of nodes and one edge in between. Now we're going to get bigger paths. Oops. Let's see. So we'll start off from Rome. Why do we start off from Rome? Well, because all roads lead to Rome, and that was cheesy. I'm sorry. Okay. So then we start off from Rome. We're going to find. So we're going to leave Rome and go to the next city, whichever one that is, right? And this recursion part is our next city bit. We're piling up a path. We're adding up the distances because the distance is the metric we want to minimize, right? We want to prevent retracing the path. So you notice that we're counting from the second element in the array till the top. Why is that? Why not just the whole array?
We already have the first.
That's right. We need to actually circle. We want exactly one cycle, right? We actually want to cycle back. So this gives you a tool for saying how many cycles or what is the cycle condition, and just instead of just being able to say cycle or no cycle, the way some of our friends in Redwood Shores would have you do. Okay. We want this query to terminate before the sun flares out and dies. So we're going to look at only paths of length 6 or less. Fairly reasonable. you find yourself always doing this when you run into NP hard problems. You have to make simplifying assumptions, you have to make this perform, and you do it at some explicit trade-off for accuracy. Okay, so we've got all the paths going out of Rome. We want to come back to Rome. And then on the way, we want to go to Milan, Florence, and Naples. Okay, so we're going to find the path. We need the to city. That's the end of the end of the cycle. It needs to be Rome 2. Then we order by distance and path, and we do this so that the result will come out anytime. The distance, they may be equal, but you need a tiebreaker so that you don't drive yourself crazy by getting different paths depending on when you executed the query. Okay. So we put in a tiebreaker there and then said limit 1. Is that how MySQL's limit works? Okay. I wasn't sure. I'm not as familiar with it as I should be. Okay, so that was it. We did the traveling salesman.SQL, and it took about 11.5 seconds, give or take, to figure out what our path should be. Alrighty, next example. Anybody familiar with Hausdorff and Besikovich? This third guy was not actually involved. Okay, so we're going to start off by making a set of points in the Cartesian plane. We're going to do a cross join on purpose. Has anybody ever done a cross join by accident? The rest of you are not paying attention. It's really easy to get a cross join by accident. You just say select star from A comma B, and then you forget to put in a where clause and bang, cross join.
On purpose.
Yeah, but I'm doing it on purpose here. Is there an explicit cross join in MySQL? No. Okay. Well, anyway, you would do this a somewhat similar way. You'd say from this comma that, and then leave out and maybe put in a comment that says cross join so nobody goes and corrects it. Because obviously it's a bug, right? Okay, points in the plane. Then we're going to union all those with that x squared plus y squared business. And we're going to make sure that it doesn't escape off into infinity, so that's where our where clause in the second branch of the union all goes. And we want to take I less than 100. Again, we want this thing to terminate pretty soon. We want to filter these. We want just the top ones, the max i's for each point in the plane that we are looking at. Then we root by I, y, and order by y, x. Now that we've got the points we want and filtered out just the ones we want, we need to display these on the screen somehow. So we have an array aggregate. This is a little bit of a weird concept. In Postgres, you can create your own aggregates, and like think of sum and count and stuff like that. In Postgres, you can actually create your own. This particular aggregate piles the stuff into an array instead of taking a sum or a count or a standard deviation. So that's what's happening here. We're going to index into a string, so it's either I. It's the greatest of I and 1. So we know what we know how big the i's can get because we said so before. They can't be over 16. If 1 happens to drop below 1, we just say it's actually 1. Greatest comes from Oracle. Does MySQL have it? Okay, great.
Are you using a parameter?
I don't think so.
Set string greatest
Ye. You're right. Sorry. Thanks, I'll fix that ASAP. Okay, so that's our display routine, and this should be part of your regression tests. Is it part of your regression tests? No, it's not part of ours either, but it may be in 8.4. Questions, comments? Yes?
First example, how efficient is it?
Which of the...
Tree.
Well, it's fairly efficient. The common table expression gets materialized just once. So you don't have these cases where something odd is happening and being executed many times. I believe it does some tail recursion cutting. So it's reasonably efficient. What we're trying to do here is get, as we normally do, is get something that works right first and performs acceptably, and then ramp up the speed. So you can expect speed increases in future versions of Postgres as this gets better.
It's not a theoretical question. We use trees in production. We obviously do it differently right now, but
Right.
that looks like it's functional.
Well, let's, can we take this off?
Sure.
No? Yeah, okay. Sorry, I don't mean to blow you off, I just have limited time here, and I think I'm already out. Okay. I'll be here the rest of today. Thank you very much.